Hello everyone. In this video we are going to talk about another topic in leg robots, and that is called zero moment point. One of you asked me to make a video about this, so here it is. The pictures and equations are taken from this paper called Ground Reference Points in Legged Locomotion by Popovich et al. And this amazing book, which I'm going to use a lot more of that. It's called the Springer Handbook of Robotics by Siciliano and Khatib. These two people are big names in robotics, okay, Dr. Siciliano and Dr. Khatib. So this idea of zero moment point, or ZMP, was introduced in 1968 by Miomir Vukobratovich. Hopefully I pronounced that name correctly. I'm not sure if I did or not. If I didn't, I do apologize. And then, what is this? Well, this is for a leg robot. This is the point where the ground reaction forces act. So basically, if you look at the foot of the robot, and you look at the load distribution, the normal forces, the distribution of the load under that, since all of these forces are in the same direction, you can replace them by a single force, a resultant force, and the place that that resultant force is acting, you can call it the zero moment point. Why we call it zero moment point instead of center of pressure? Because that's the definition of center of pressure, right? That is exactly the definition of center of pressure, right? So why do you call it zero moment point? I'll show you. But the important thing is, first of all, the surface has to have sufficient friction to keep the foot from sliding. Okay, so here we don't assume that this foot is stuck to the ground or anything. And this notion is applicable to both single and multi-leg robots. And the good thing about it is it basically resolves, or I can say shrinks down all of these distributions to a single point. So instead of looking at all this patch, this contact surface, and all this distribution, you summarize into a single force act at a single point. Okay, yeah. So if you look at the robot, when it's walking, you can have the mg force, you can have the ground force at the ZMP, and you can have these inertial forces which are due to accelerations ma, right? Okay, so let's go ahead and look at some mathematical definitions. So the center of pressure, or COP, is basically, and some people use a small o, so let me use a small o, is, as I said, if you have the flow reaction to be on a finite number of contact points, pi, I goes from 1 to n, and the force at each one of them is F equal Fix, Fiy, Fiz transpose, then COP can be calculated by what? The point COP can be calculated by summation of a weighted what? A weighted number of PIs here, where PIs are what? Are the location of those contact points. P is the location of center of pressure, and alphas are the weights. How are these weights calculated? They are calculated by Fiz divided by total summation of Fi's, which is Fz. Okay, so if you write it, this is going to be what? This is going to be summation of basically Fiz times Pi divided by summation of Fiz, and that's exactly the definition of a centroid, but not centroid of mass. This is a centroid of force, so we call it what? We call it center of pressure. So these alphas are the weights. Now, one important thing is all of these forces have to be positive or zero, okay? No force should be negative. This is an important inequality. All of these weights, alphas, should also be always bigger than or equal 0, and some of them is, of course, equal to what? Equal to 1. Okay? So this is the definition of what? Center of pressure P. And also, this is the definition of the zero moment point. Why? I'll show you. But the important thing is these two are the same, ZMP and center of pressure, as long as the surface is what? Flat horizontal surface. And you see that the only component of the contact force that matters is the Z force, the upward force. Okay, these guys. The X and Y, the horizontal ones, don't matter in the definition of that. Now, before I talk about why we call it zero moment point also, let's talk about a few things. First of all, if you look at this definition, this weighted sum of these PIs, this definition tells you something. What does it say? It says that if you have the convex hull of the contact points and you call it the support polygon, then clearly the ZMP has to be inside the support polygon. So if you look at the robot foot from the top, if you look at this view, but from the top, so let's say this is the foot from the top view, and let's say this finite number of points are these. Okay, yeah? Then if you create the convex hull of all of these points, which is basically this one, your center of pressure should definitely be what? Somewhere here, inside the support polygon. Okay? So that is obvious from this definition. And so that's a limitation also, that the ZMP should never leave the support polygon, and if it does, then this condition Fiz bigger than or equal 0 might not be valid. Okay, so definitely your center of pressure should be inside the support polygon. Now, why do we call it zero moment point? Let's answer this important question. So how do we calculate some of the moments about this point? So tau about this point is equal to summation of pi minus p cross fi, right? Where again, look, so at each one of these points, if I look at this view, at each one of these points, this point here is your pi, this point here is your p, and the force here at this point is Fi. Now it has XYZ component here, we are just showing the Z of it. And so if I subtract Pi minus P, it gives you this vector, this R vector, this arm, right? This guy is Pi minus P. So if you cross product that vector by this force, that's the moment. And then if you sum it up over all i's, that's the total moment. So if you break it down, because the P, I, and P and F, they have X, Y, and Z components, then you get the total X moment about this point, the total Y moment, and the total what? Z moment about this point. Okay? Now, as I said, if the floor is horizontal, then the Z component of the center of pressure and the Z component of the other contact points, they have to be the same. If that's the case, what's going to happen here? Well, look, this guy is going to be what? 0, huh? And what? This guy is going to be what? 0, because PIZ and PZ are what? The same. So what happens to these two components now? These two are also 0 because of the way that we defined P. If you look at this definition of P, right? Let's write it again. P equals summation of Pi Fi divided by summation of Fi, right? Yeah? So if we multiply both sides, this is going to be like that. And now what? Now, if you look at the X and the Y component, let's say the X component, so this is X and this is X, right? And bring them into one sigma, you see that's exactly this guy here. So if you subtract, instead of saying equal, and set it equal to 0, you see this term is going to be 0. Or if instead of X, you make it Y, and again bring them to one side, then you see that's this guy here. Okay, so clearly the tau x and the tau y has to be what? 0, but the tau z does not have to be 0 clearly. Okay, so you see that about the center of pressure, the horizontal components of the moment, Tx and Ty are 0, not the vertical one, Tz. That's why we call this point what? 0 moment point. And when we say 0 moment, we are not talking about all components of moment, just the horizontal one. So another way to define the ZMP is what? This is the point on the surface about which the horizontal components of the moment is equal to 0, or you can say the horizontal components of the moment are 0. Okay, that's another way to say that. Or in other words, the total net moment is always parallel to g vertical direction. So you can say T of the ground at point ZMP, the horizontal components, which is both x and y, these are both equal to what? 0. That's another way to define the 0 point moment. Okay, one last way I want to represent this ZMP to you is, since I only have 3 forces on the robot, right? The ground force, the mg, and the inertial forces. And here we are using D'Alembert principle, and we assume that the dynamic system is equivalent to a static one if these inertial forces are considered. So about any point, including ZMP, sum of the total moment should be equal to 0. So the total moment of FGR, MA, and MG in any direction x, y, z is 0. Now if you look at x and y directions, remember that the moment of the ground forces about ZMP, x and y component are both 0. That means the total x and y component of MA plus MG about ZMP should also be equal to 0, and that is this second definition that you can see for ZMP. Now, let's go ahead and talk about how to calculate the coordinates of this ZMP, which is a point on the xy plane. So we should calculate x and y of the ZMP point. So here we go ahead and consider the components of this robot, right? So we call this, let's say, component 1, component 2, component 3, 4, and so on. And if we show the information for each segment with index j, for instance, the mass of it with mj, the centroid with cj, the inertia about the centroid matrix ij, and the rotation matrix of that with rj, then the total linear momentum of the robot and the total angular momentum of the robot with respect to origin is going to be given by, so the total linear momentum is summation of m times the acceleration, the velocities of the centroids. J goes from 1 to n. We show it with p, vector p, and vector L, which is the angular momentum of the entire robot, is going to be what? Is going to be the Cj cross Mj Cj dot. Remember, this is the linear momentum of what? The jth component. If you cross multiply by position vector, that is what? That is the angular momentum of that jth component due to motion of the centroid, plus, of course, what? The I omega term. Remember, the I omega is the term due to what? Due to the rotation of particles of the ith component about the centroid. So if you look, this is my origin, or let me show you in this picture. This is my origin. If you look at jth component, one of them, let's say this head, this is the centroid of that head, okay? And the centroid of this head has some velocity, which we call by Cj dot, and it has this position vector Cj. So Mj Cj dot is the linear momentum of that centroid. If you cross multiply Cj by that, that is one component of the angular momentum of this head, but also these individual particles that you have on this head, okay, they also move about and they rotate about the centroid because this component has some omega I, right? It has a spin and it has this I, the inertia matrix. So I omega I, right? That total thing is basically equivalent to all of these individual angular momentums of these particles about the centroid. So here, these are about the centroid. We add it to this term, so we get the total angular momentum about what? About origin. So the reason we are adding this first term to I omega is that is the total moment about origin, not the centroid. We are writing equations about the origin here. So that's why it is added. And you might say, what is this R and R transpose? This is to transfer your inertia matrix from attached to the body frame to what? To the origin. So this is with respect to what? Origin. This is II, but written with respect to origin with respect to the inertial frame. Origin, inertial frame. Okay? If you followed my robotics lectures, you know about that. So this is the total angular momentum of the robot about origin. This is the total linear momentum of the robot. Now, if this robot is applied to it, the external force F and the total moment tau about origin, then of course the changes of P and L with respect to origin can be given by Newton-Euler equations, where sum of the forces equals P dot. Now sum of the forces equals F plus mg in general, right, equals P dot. So if you want, you can take that mg to the other side, so F equals P dot minus mg. And if you take some of the torques about the origin, tau equals what? Equals the time derivative of this linear momentum of the system total. And you also need to add or subtract this term. This term, if you want, you can add it here. That is what? That is the moment of your mg. Okay, so this is tau of the external forces, except mg, this is the tau of mg. Okay, this is tau due to mg, right? Because this point here has this vector c, and c cross mg is going to be the moment of the mg with respect to the origin, which, as I said, you can have it on this this side and then take it to the other side. Now this is equal to also what? This tau is also equal to what? Here we are doing from here to here, we are doing a transfer of moment. This t is with respect to origin O. But if we want, I can also write it as t with respect to the ZMP point plus what? P cross F. What is P? P is the position vector of that ZMP. So this vector from here to here, this vector is what? P. Yeah? So if my external forces F are at any point, okay, the moment of them with respect to origin and the moment of them with respect to the ZMP point, there is a difference between them. What is the difference? The difference is P cross F, right? So here I'm doing transfer of moment. So these two are equal, yeah? And these two are equal. Where here, this G vector that you see as a vector, this is the vector of gravity, which is 0, 0, negative G, and G here is in the Z direction, negative G transpose. Good? So these are Newton-Euler equations. Now, what do we do? Now we're going to replace. Remember that from this top equation, tau Zm equals what? Equals tau minus Pf. Let me do a little bit fast cleaning here. So from here, we are after this tau ZMP, so we take this Pf to the other side. So it becomes tau minus Pf, but remember tau itself is what? If you remember, tau is L dot minus Cmg. So what we can do is basically bring this to this side. So it becomes L dot minus Cm cross G, C cross Mg minus Pf. And that is exactly what you see here. That is L dot minus Cmg and then P cross F. Now for F, I replaced it with this guy. Okay, and you can see it right down here. You might say why the order is backwards. Instead of P cross F is F cross P, because I took it to the other side. So it became negative P cross F, which is the same as F cross P. And that is what you see here. Now, if you expand this equation for x component and y component, the x component of TZMP will be L dot x plus mgy plus P dot y, where px, py, and pz are the components of this p, right? This p is what? This is px and py and pz, and this tau ZMP is tau of ZMP and x, then tau of ZMP and y, and tau of ZMP and z. Yeah? So the x and y component of that are going to be given by these, but remember that the total moment in the x and y direction about ZMP is what? 0. Remember this? So these two have to be equal to 0. Now, if you look at these two equations, the only unknown in these equations are what? Yes, what we are after is px and py, the coordinates of the ZMP point. If you solve for these two unknowns from these two equations, these equation 8s are the locations of what? The x and y location of the ZMP point. Here I did some cleaning, and here, of course, m is the total mass of the robot, so I added that for you here. Okay, m is the total mass of the robot, and c, if you have it, it's the centroid of the robot. So here m is that. X, y, and z, here we only see x and y, but x, y, and z are the coordinates of this centroid. Okay. And then px, py, pz, as I said, these are the coordinates of this ZMP point. And these p's that are, they have this different font. These p's are the momentum of the system, linear momentum, and these l's are the angular momentum. Okay, so now let's move on. Let's look at some simplified scenarios for these equations. So these are the general equations for px and py. And under certain scenarios, you can get simpler versions. So if all you care about is the x position, because you are looking at the motion of the robot forward, backward on a flat surface, and assume that there is no net moment condition about the centroid, so the robot basically keeps its upright position as it moves on straight forward, right? Under this feet, where is the ZMP, right, which is only x, then all you need to deal with is this top equation. Since the robot is keeping its upright position, no net moment about centroid, the angular momentums are all 0, the derivative of them, or they are constant. So this guy is 0, this one is 0. Then about the px dot and pz dot, remember p is the total momentum of the system, which can also be written as times the velocity of the centroid c dot, okay? And if that's the case, then P dot is going to be MC double dot. So the x component of that, Px dot, can be written as M times x double dot. And Pz dot can be written as Mz double dot. So here, you're going to replace them with mx double dot and mz double dot here. And for the moment, let's assume that the robot, as we said, it's moving on a flat surface. When it's on a flat surface, that means there is no z for the centroid. The z of the centroid stays in the same place. So the z double dot is also equal to 0. So this term is 0. So what you end up with for px, which is the same as x of ZMP, that p of x is going to be what? It's going to be mgx, correct? Plus pz times mx double dot divided by what? By mg. Which if you simplify, you're going to get x, and you're going to get what? Plus pz times x double dot over g, which is the same as this formula. Now you might say there is a negative and there is some difference. So here positive pz is turned into negative zcm. Is that correct? Yes. Why? Because pz here is the z of the floor, the z of this flat floor here. Okay? And z of cm is z of the centroid. And they're both measured from the origin. So if we set the origin here at the same height as the centroid, correct? Yes? Then P of Z, which is measured from here, is going to be that much, right? This is P of Z in this frame. And how much is it if this height here is Z of the centroid? Okay, Z of the CM, of course not measured in the same frame, but measured with respect to the ground. Then you see these two are the same thing in magnitude, just opposite direction, so I can write it like that. And if I do it, then I get this formula. Okay, so this formula is what? This formula is your x of the centroid. But if you want the 2D version of that, where you have both x and y, then you use these equations 8. Now, the reason that I use this different measurements in this z measured from this bottom instead of measuring from that is to reconcile it with another way that you can derive these equations. If you look here and make a simplified model of the robot as it is moving on the ground, and consider it like what? Like a simple mass, okay, which is basically on a tilting table here, shown with this table in red. Okay, so you can simplify your robot to something like this, where this bottom of the table is the foot of the robot. This is the height of the centroid, right? Or the height of the waist, actually. And this centroid can move on this left and right, okay? So it can have in general acceleration x double dot. Then if you calculate the total moment tau about this ZMP point P, so total moment about the ZMP or P is equal to, and here we go counterclockwise positive, it comes from the force mg here, which is going to be clockwise, so negative mg, and the distance here is x minus p. And then the inertial term here is always in the opposite direction of acceleration, so it is going to be in this direction. That is going to be mx double dot, and clearly for this point it is positive or counterclockwise, and the moment of it is mx double dot times this zc that. And since this total moment has to be 0, okay, for the horizontal direction, which is in this case out of the board, whatever you might want to call it, you might want to call it y, correct? Because y is out of the board here, x is in this direction, and z is upward. So since this total moment y is equal to 0, from here you should be able to calculate the position of the ZMP point P, which is going to be x minus z of the centroid over g times x double dot, and that is the same formula that we derived earlier. Okay, yeah, so you can derive it in 2 different ways. Now, keep in mind, if upward acceleration is present, and as this guy moves, it does not necessarily move on a flat surface, or it goes up and down, then you have to also include a z double dot here in this denominator, and that comes from this guy here. Okay, And if the robot is tilting forward and backward, then these terms are also non-zero, and you have to include them as well. So in general, if we want to find the location of the zero moment point, we can use these equations number 8. And this equations number 8 can give you something interesting. Other than the simplified version, they can reveal a bunch of other things. So let's look at some points that you can get out of them. 1. If you look at the simplified version of that, which is this equation 9 or 10, you see that if the robot is stationary, okay, here you can say the cart, or in general, you can say the robot. If the robot is stationary, okay, so let me change it. When the robot is stationary or moving with a constant acceleration, what happens? Then the x double dot term becomes 0, and if that's the case, the location of the ZM point becomes the same as the location of the centroid, or it's going to be the projection of the centroid onto the horizontal plane. Okay, and that's kind of expected. Now, on the other hand, if you look at this equation number 9, remember we said that this ZMP point should be always inside the what? Inside the support polygon. Remember when we talked about it, said that it should be inside the polygon, right? Physically. But if you look at this formula and this mathematical computation of that, let's take a look here. If this x double dot is a big number, okay, if it's very big number such that basically this term will dominate this one, okay, and bring this x of ZMP outside the polygon. So basically, let's take a look here, back to this picture. All this p can change physically is from here to here. But if this x double dot is a very, very large term, what happens? Then, let's say, for instance, this x of the centroid, if we measure that, let's just go with some numbers. Let's say this is 2 units. Okay, so this guy is 2. And z over g is something, let's say this is, for instance, 1/2 magnitude-wise. And this x double dot is now what? And here we have some dimensions for this foot as well. So let's say this is 0.5. So this end is 1.5. And if you calculate p, it is 2 minus 1/2 times x double dot. And what I want is x double dot is bigger than 1. So it is like 1.6. Then you get 2 minus 0.8, you get 1.2. And 1.2 means it's here. So you see your center of pressure, which in this case the same as your ZMP point, falls outside the support polygon. So although mathematically it can, physically it can't. And why is it that mathematically it can? The reason is when you calculated these two values for px and py, especially px, you did not enforce this important condition that all of the individual forces that are applied at each point, they should be positive. We have never forced this, and we kind of assume that like these legs are basically glued down to the ground, not really creating a positive force because they are pushing on the ground. Okay, so although mathematically possible, physically not, and that is one of the shortcomings of this approach. As we'll see later, it has some shortcomings. One of them is what? That it can go outside the support polygon while physically it cannot. And the other thing that you have seen so far is the calculations we have done is it's only limited to flat surfaces. And for flat surfaces, it's the same as the center of pressure. Now, in many cases, the robot does not move on flat surfaces, where the ZMP definition should be different than the center of pressure, okay? And so we are not going to go with this original definition, this one. We cannot use this original one here, because this is for center of pressure. So we have to go with an alternative definition. And that's why in the literature, because of some shortcomings of this ZMP approach, there are some alternative methods that are proposed, like there is one called foot rotating indicator, which I'll try to explain in a separate video, or this one, centroidal moment pivot, or CMP. So these are other methods to describe the point at which, or they are not the point at which the force is applied. They are a little bit different in definition, but we use them for checking the stability of what the biped or legged robot in general. Because as I'm going to show you in a second, we use this ZMP to what? So far we said how we calculate it, but what's the use of a calculation of it? The use is to make sure that the robot is stable, it doesn't fall, it doesn't tip over, and to also, with that stability, kind of determine what kind of motion the robot can have, so that with that kind of motion, it is not going to tip over. Okay, so we have learned two important things so far. Let's talk about the last thing, and before we go to stability, and that is if we have sensors that can give us the values of px dot, py dot, pz dot, and L dot x and L dot y, we should be able to calculate px and py, okay? And that's why these formulas that you see for px and py, we call them what? The value that you get for that, we call it the computed ZMP, okay? So those formulas, these equations 8, we call them computed. Compute based on the model of the robot and sensor data, we can have what? Computed ZMP. Now, what kind of measurements do we need? First of all, we need to have encoders. So they tell us what? They tell us these different angles that the members have. If they tell us those information, if we have a physical model of the robot and these angles, we should be able to calculate the location of the centroid at each point. And the location of the centroid is important. As you can see, we need the x of it and we need the y of that. So we need to know the x and y of the centroid, as well as what? Of course, this PZ, or you might say this ZCM. So we need to know the location of the centroid. The other thing we need is the acceleration. If we can have the linear accelerations or these angular acceleration terms, which are related to external forces and to external torques, we should be able to what? Measure these guys. So if we have a sensor that give us all the XYZ components of force and the XYZ components of torque, we should be able to calculate these P dots and L dots. And so that comes from what? Typically comes from a foot sensor that has 6 axes. And that gives us F and tau. So if you have this model of the robot, as I said, the encoders and these 6-axis sensors, we should be able to use equations 8 and compute the ZMP. That's why we call it computed ZMP. Good? So far, this is all about calculation of ZMP. What is it? How do we calculate it? Now, let's talk about the applications of it, which is more important. So where would you use it? The first thing is, in many times in the literature, ZMP has been used as a metric for what? For stability of the robot for against tipping over. Okay? So, in a leg robot, when would you lose rotational equilibrium and you tip over? When basically the foot during single support, and by single support means one of the legs of the robot is touching the ground, the other one is lifted to take the step to do the gait. So during a single support, you only have one leg on the ground. Then you have basically an unbalanced moment. And what's the result of the unbalanced moment? The result of the unbalanced moment will make your lift or your foot to be lifted off the floor, as you can see here on the right, instead of being this stable position on the left where the entire foot is in contact with the ground, and the ZMP, as you can see, is inside this polygon, right? Of course, you don't see the polygon, you only see one side of it. But if the robot is about to tip over, right, or like us, the bottom, the heel of this foot is going to be lifted, and the ZMP is moving toward one of the edges, in this case, the forward edge. So you see the ZMP goes to the very edge of the support polygon. And that means what? When it goes on that edge, means you're about to tip forward. If it comes all the way down to the left and the ZMP comes here, that means you're to tip backward, right? So as this ZMP is further away from the edges of the polygon, that means more stability. As it gets closer to them, that is what? That is a smaller stability. So we can use that as a margin of stability. Okay, yes? And also, as I said, if we go back here, if we pick the centroid of the robot to move very, very aggressively forward, so a big X double dot is present, that makes this P to not only, you know that when we are designing this robot motion, if we choose this X double dot to be big, that, as I just showed you, can cause this zero moment point to go outside the polygon, either here or if it's backward, go here. And any of these means what? Absolutely unstable. If it is on the edges, you're about to tip over. If it's outside, then you're definitely falling. Okay, you're definitely tilting. Okay, so you see that because this one can only be between two limits, A and B, which are measured by the left side and the right side of this foot. That gives us some limits on how big this acceleration can be. Okay, so the motion of the body can be planned based on the limits that you have on the zero moment point, how far it can go as long as it stays inside the polygon. Okay, and that is what very critical. So you can use it as a method of stability and design of the motion. And some robots in the past have been used in ZMP skim, as you can see down here, 4 of the major robots, like this, I hope I can pronounce it correctly. It sounds like Johnny, hopefully, 2000, HRP2L 2001, WL16R 2003, and this Hubo humanoid in 2006. Another one, famous one, is Osimo. Okay, and these robots, many of them from Japan, and they are legged. You see, they are mostly just biped. They have been stabilized, and the motion for the motion control of them was designed based on the ZMP. Okay, and these ones that were designed and controlled based on ZMP, they had some common features. One was there are at least 6 fully actuated joints for each leg. The joints were position controlled, and the feet were equipped with 4 sensors, as I said. And that way they can compute the ZMP and they can control the robot through the joints. Okay? Yeah. And when they say 6 joints, means at the hip, at the knee, and at the ankle. So at least there are 6 of them in the robots for most of these to, or all of them, to get the robot under control. Now, let me explain a little bit more about the last item that I said, and that is ZMP-based walking pattern generation. Okay, which I said based on the values of ZMP, you can design your motion. So in modern implementations of this method, what they did was the body motion, which is like X double dot and so on, they are used to realize prescribed ZMP trajectories. Okay, So if you know where your ZMP is going to be, if you know for each one of these feet where the ZMP is going to be, how it is going to move forward and backward within the support polygon, based on that, they determine what? They determine the body motion, as I said, terms like x double dot and so on. So this way, the foot trajectories, they were prescribed by the ZMP limits, and then using inverse kinematics, the leg motions were defined, right? Because if you have this leg like that and this foot can only, for instance, go from this step to the next step, it comes like here, right? So it moves like this. Then this is like a 2 degree of freedom robot, and this is like the end effector. So if it moves this much, then you can calculate what, assuming that this point stays the same. Let me change this. So something like that, for instance. Then you can what? You can calculate these changes in these angles, right? This one and the difference between these two. Okay? Now, one important thing, as I mentioned, is they first determine the profile of the support polygon. They determine that from the foot trajectory, like you can see here in this picture, in this gray band. So this gray band is the support polygon and where it can be. Okay, yes. And the width of this from here to here, is determined from what? From the foot geometry, how wide the foot is. And these guys are determined based on the steps that the robot is taking, from a touchdown time TD to a lift up time LO. So if they can determine these gray bands, which is where the foot of the robot is going to be, yes, the support polygon, then any curve that is inside this gray band could be the curve of change for ZMP. Okay, so it could be exactly in the middle, it could be a little bit off toward one edge, it could be off a little bit toward another edge. This moving toward the edges is going to change the stability margin. Okay, so if you have a stability margin, then you say, for instance, I don't want to get anywhere close to the edges with, let's say, this much of offset. Then you go ahead and draw this parallel to the boundaries. Let's call it epsilon. They draw this parallel to the boundaries, epsilons, on both sides. And your curve for ZMP, which is this brown one, should stay within that. And as I said, once you know that one with inverse kinematics and with the equations of computed ZMP, you can calculate how the other joints can move and how much of acceleration you can have so that you're always inside. Okay, so hopefully this introduction to the idea of zero moment point in leg robots was useful to you. There are lots of other things that we can discuss about them, about exactly what the details of this ZMP-based walking pattern generation, and about these alternative metrics like FRI and CMP, but that is beyond the scope of one lecture here. So I'll stop this video, and hopefully in another video I'll talk about those. Thank you so much for your attention. I'll see you in the next video.